just interrupt me or ask in the chat. I have now 2 computers in front of me. I will teach sitting so that I can also use this mouse to point important things. Some people pointed to me that when they follow remotely, it's easier for them if they can see the mouse. And since now we are only few in the classroom, then we can also do this sitting very informally. So first of all, I hope that you are all fine, that everything is under control. Basically, from now on until we hear otherwise, we're going to continue this course completely remotely, which shouldn't be a big problem because the big part of the course was remote anyway. Everything should be online. After we are done with this, I will put the videos of both this lecture and the previous lecture online. And next week and the week after that, I'm going to stay online after both of the classes so that you can ask me any questions regarding the hands-on that we are going to do or regarding anything else that you have problems with. Okay, so today we're going to take a small break from solar physics. We will mention it very, very briefly, and we're going to talk about model fitting. Model fitting is something that I like a lot, and that is always interesting for me to think about and to use. And I will try to pass some of this passion on to you and to explore this together. Okay, so far we were talking mostly about the observations in theory, or if you want to say modeling. When I mean modeling, when I say modeling, I usually mean this point 1 here, right? We want to use theoretical models which are provided to us by other people, which can be a result of simulations, which can be a result of other people doing some other theoretical considerations. We want to calculate some observable from there, and we want to compare that with what we observe, right? And for example, now I'm going to use some examples of the projects that you are doing. So for example, I know that Momo was studying H-alpha, that he was calculating H-alpha line profile from various empirical model atmospheres and then inferring some properties about H-alpha from there. And that's one goal of modeling. In principle, sometimes you might even not want to do that. Sometimes you will just want to do your observations and then present your observations, and that's already a big scientific contribution, especially when these observations are specifically made to detect something or something like that. But however, very often, and especially with DKIST, it is very important for us, is that we will want to infer something from the data, something quantitative. We will want to measure. I hesitate saying measure, but I also, measure is very easy for you to understand what measure means. In this context, it means, figuring out what, for example, magnetic field is in the pixel that you're looking at. What is the plasma velocity at the pixel you're looking at? What's the temperature there, or something else, right? An essential part of that is fitting some model, and hopefully that model will have a physical background to the data that you have observed. And the reason why that is very important with the DKIST, okay, is this really a reason? It's important to know these things because with the DKIST you will get a lot of data that will be very, that will be a fitting data to draw quantitative conclusions from. So all these Stokes spectra resolved in time, space, and wavelength can provide you with a lot of information about the physical parameters in the atmosphere of the sun. And NSO recognized that importance, and relatively recently, a year ago or more, or even more than that, they established this level 2 efforts, and quite a few people here are supported or are, a part of this level 2 effort. And by level 2 we mean going beyond the observations themselves and obtaining some physical properties of the observed atmosphere. And these level 2 projects aim to somehow automatically provide it for you. So at some point, if you apply for observing time with DKIST, you get the observing time with the DKIST. If your observations are not something super extraordinary in terms of their setup, then in that case we will probably provide this so-called level 2 data for you, which means we will do some basic inference from your data and give you these results to work with. However, you should not treat this as God-given quantities. You know, very often we go to, for example, SDO or some other telescope or mission that delivers observables, as people wrongly call them, and then we just take magnetic fields, velocities, and stuff like that, and just use them without understanding how these were obtained. So in the first part, here is Ali laughing, smiling at my conclusions here. So in the previous 3 or 4 lectures, we were basically studying line formation, which means we were studying how the physical quantities generate the observed spectrum. Now we want to talk about the inverse process, basically. We want to talk about how to go from the observations to the physical parameters once we have established our model. And today we're not going to talk about the sun at all. We are only going to talk about general picture, and then we're going to apply some of these concepts next week. I mean, depending on where you are now, it will maybe be the week after that, because we are going to repeat these hands-on exercises 2 times. And then finally, after the all spring breaks are done, I'm going to take one class to really tell you in detail how these spectropolarimetric inversions work and what is happening there and what is physics underneath and what are the troubles and so on and so on. Okay, so most of you probably already did some model fitting, and here are some examples. And I always I want you to pay attention to the semantic construction of these sentences, which might be wrong because, as you know, English is not my native language. But here are some of the examples that you probably even did at some point in your life. So, for example, the way we detect, for example, the way we study the black hole in the center of our galaxies, we look at the trajectories of the stars that are circling or ellipsing around the black hole. Then we track the positions of the stars in time. Then we fit that with an ellipse, and that way we can figure out the location and the mass of the black hole. Or, for example, if you people who recently, well, is it recently? It is recently got the Nobel Prize for the discovery of the acceleration of the universe. They were fitting some quadratic function to the dependency between the distance modulus and the redshift of the supernovae in order to confirm the fact that the universe is accelerating, right? Or my favorite example, something that you maybe even did already in the high school, is to use a pendulum with different lengths and then fit the dependency between the square of the period of the pendulum and the length of the pendulum in order to determine the gravitational acceleration. Then you can go to more complicated models. For example, one of that is you can use a cosmological model, which depends on multiple cosmological parameters, and basically fit the map of CMB, or actually the power spectrum of the CMB, in order to determine these cosmological parameters, and that's what people from Planck collaboration are doing, for example. And then finally, the solar physics example, what you can do and what we ultimately want to do is to fit some line formation model to the observed Stokes spectrum in order to infer magnetic fields, velocities, temperatures, and so on and so on. So the sentence always looks like this. We fit some mathematical expression to the observed data, right? And this mathematical expression usually has to result from some physics. It has to have justification, right? And now I'm gonna to illustrate this, I'm gonna give you a very personal example. So when I was a kid, so at the end of my elementary school, in Serbia, elementary school means end of elementary school means age 14, 15, and at the beginning of my high school, I was going to this, I like to call it boarding school for nerds, which was very close to my hometown, which is basically an institute, which is something similar to our REU, except it's for younger people. So you go there and then they teach you various cool scientific stuff, and then you can do a small project through the summer and so on and so on. And one of the first things that we did there involved some model fitting. So we were doing something, I don't know, it was probably this pendulum exercise that I was mentioning before, and the goal was to do these measurements, to plot these things, and then to fit. And back then there was no Python, I didn't know about the IDL, I didn't know how to code, so we were using some programs which had some graphical interface, and the ones that I was using were Origin, which some of you maybe still know, and Table Curve, which was, I don't even know if that exists anymore. And then I remember looking at the data, and trying to fit and thinking about the fact how frustrating it is that I have to give the code the function to fit the data with. I couldn't understand why cannot the code figure out on its own which function it needs to use. Maybe in this particular case the third order is better, maybe in this case the fourth order is better, maybe in this case linear order is better, and so on and so on. And that obviously tells you that I was missing the point of the exercise, because fitting on its own means nothing, right? If you see a data and the data has the shape of parabola or the shape of the linear function or something like that, of course you can fit it with the function of your choice, but the question is, will that tell you something? And sometimes we need to fit scattered data with various functions, for example, because we want to interpolate or because we want to extrapolate or something like that, or integrate something. But what I want to talk about here is fitting with physically motivated functions. So every function that we use will come from some physical motivation. And in order to do this fitting process, we need this model, which needs to come from very careful considerations. We need to have our measurements. These measurements need to have some errors or uncertainties or noise, whatever you use. And then we're going to need something else. So let's start talking slowly about it. And let's, before all these things, basically, I want to show you the paper where I learned all these things from, and the paper that I definitely recommend that you all read at some point in your life. It is a paper which only exists on arXiv. As far as I know, the authors are David Hock, Joe Bowie, and Dustin Lang, who are all very accomplished astrophysicists working here in the US and in Canada. They are all cosmologists, or you could say galaxy people. And the goal of this paper has nothing to do with astrophysics. It literally teaches you what are important things to know when you want to fit the model to the data that you have. And this guy, David Hock, is for me one of the smartest people that I have ever seen. And he also has a lot of nice YouTube lectures and stuff like that. And he's really, really lovable person who knows a lot, and you can learn a lot just by, analyzing digital content that he created. So this paper here, I will post the link on the web page, and I really recommend that you read it at some point and try to reproduce some things from there, because it's really, really worthwhile. And I can't recommend it enough. It's much more extensive and much more informative than any of my lecture will ever be. But let's try to approach that a little bit, shall we? So let's start from the simplest possible example. So we are looking at the chunk of the sun, and we, for example, are assuming that the intensity or the number of counts that we receive from that chunk of the sun is not changing with time, or at least it's not changing fast enough. So we repeat the measurement 20 times and we get different results. And you know now that these different results, which I'm listing here, which are all roughly around, what is this, 10,000, right? Some are more, some are less. We know that basically the noise or the scatter or the uncertainty of these measurements comes from basically the photon noise. It comes because of the randomness of the counting process, so to speak, right? And now what we want to do is we want to figure out the true value. And the first thing is that we cannot know the true value. I can't say, okay, true value is this, full stop. We can only estimate it. And the thing that we are basically trying to estimate is we are trying to estimate the most probable value of the true value in some limits. So this immediately implies that what I'm aiming to find out is I'm aiming to find some value plus minus something, right? And in this case, if we're giving this true value without any uncertainties, without any limits, it's completely meaningless, right? If you are measuring the number of counts and you tell me it's 10,000, you need to know some measure of uncertainty, right? And of course, I'm not suggesting that you now do this following procedure that we're going to do, that you do it every time when you are using your CCD. For your CCD, it will be completely fine to estimate the uncertainty as the square root of the number of counts. But this is just a very simple example that will be relatively easy to generalize to more complex cases. So what is unknown here is this constant value, and that is our model. So our model here has only one parameter, right? And it is this value, which is, I'm going to call in the remainder of the talk y Y true, right? And the measurement uncertainties are also part of our model. It is very important to know your uncertainties and to know which distribution function they follow. So if I plot the distribution of the measured values, it looks something like this. And here I'm plotting 3 possible values for the true value. And probably most of you are guessing that since I'm a very lazy and obvious person, I chose 10,000 as the true value, which I did, but it's not super obvious from this plot, right? You can see that the true value should be something around 10,000. You all know, or you are guessing, that basically the most probable true value will be the mean of all these observations, but it's not so obvious. If I increase the number of measurements, it becomes a bit more obvious though. So I just want to use this plugin here to stress that increasing number of measurements always helps you infer the parameters of your model. And this is also true. This is, for example, now I'm jumping back to solid physics, but this is, for example, why I always prefer nice spectrograph data to the nice filter graph data. Even though filter graph data has amazing pictures and so on and so on, spectrograph data, if you want to draw quantitative conclusions, just gives you a lot of nice, evenly spaced, valent measurements where you can obtain nice shape of the spectral lines and so on and so on. And that's something that we're going to do at some point, right? Ryan agrees to, right?
Are you dissing IBIS?
No, I'm not dissing anything. I'm just saying that for diagnostics, maybe spectrographs are a little bit easier to use, so to speak. So let's now start showing the equations, which are my favorite thing in the world. So what is our model? What is the mathematical representation of our model? Well, we have our measured value, which we have 20 realizations for, which is equal to the true value plus some uncertainty. Right, and this uncertainty is basically what we call noise. And in this context here, the noise follows this function here. So it's a random variable extracted from this distribution here, which we call Gaussian distribution. And I'm aware here that I'm using Gaussian in a different way than everybody else. So usually people are going to have an extra 2 here the denominator, an extra 2 in the, square root of 2 in the denominator, and 2 sigma squared here in the exponent. I just like using sigma and sigma, so sorry about this. I probably should have put an extra 2 here, but it's just a difference in interpretation. So what I want to stress here is that since the noise is random, it implies that our measured value is a random number. And the fact that it's very close to 10,000, it still doesn't make it non-random, okay? So we have a set of random variables, a set of measured values which are random, and from that we are trying to infer maximum probability of something. We are trying to infer the maximum probability of this quantity here, y, which is not a measured value. I'm sorry, it should say true value, so I should correct this. So don't pay attention to this thing here. Okay, then we can see that the probability, and now let's get used to this notation that I'm using here. So what is this P, and then in brackets we have yi, vertical line, y true equals blah, 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 blah. This thing here means probability of getting the value yi given the value y true. So if y true is 10,000 or something like that, to get yi equals to, I don't know, 10,001 is going to be, and then Gaussian function here on the right, where basically the probability, the probability distribution or the probability density is going to depend on the width of the spread of my Gaussian function here. And this is something that follows from basically follows from the assumption that in the most cases our errors are normally distributed, right? And Kevin told us a few lectures ago, actually more than a few lectures ago, that in the case when we have a lot of photons, that it's usually true. Strictly speaking, it should be a Poisson distribution, but since sun is so bright and we usually measure a lot of photons, we can assume that it's Gaussian. However, pay attention, maybe if you're doing some model fitting, maybe in your particular case, the models are not going to have Gaussian distribution. Then I'm going to use bold Y to denote a vector of observables. So bold Y is the set, is the whole array, Y1, Y2, to Y20, right? And obviously the probability of obtaining exactly this set, given the true value Y true, is just the product of all these probabilities up here, right? Because I'm repeating measurement 20 times, right? So, what are we looking for now? Naively or intuitively, we're going to say, well, okay, I can write down this probability of my measurements given the true value. What do I have to do now? Well, the only thing that I have to do now is I have to find the maximum of this probability for various values of Y true, and I have solved the problem. Strictly speaking, that is not true. So we need to find something else. We will see that under certain assumptions, this is going to be true. And to understand this fully, we're going to have to use something called Bayes' theorem. And basically, the way to understand why we need something else is to read the meaning of this sentence here. This equation here. This equation here says probability of getting this set of measurements given the true value Y true is blah blah blah. Okay. So we are not looking to maximize that probability. We are looking to maximize the probability of the true value Y true given our set of measurements. And to understand the difference between these two statements, people have a lot of examples, and sadly most of these examples use some sort of testing for diseases and stuff like that, which is something that I'm going to try to avoid today since we are hearing about the diseases all the time. So I came up with a little bit foolish but hopefully still correct example, okay, which is going to illustrate the difference between the so-called prior probabilities, likelihood, posterior probabilities, and it's going to imply the use of Bayes' theorem, and it's going to teach us what we need to do and how to conduct proper inference. So this is the detective story. The detective story goes like this. There was a pack of cashews somewhere in NSO, and one day it was missing, right? And let's say that it was a public property, so it's important that it was missing because somebody took it without other people figuring it out. And then what we figured out is that there was a print on the next to the cupboard which corresponded to these specific Asics Onitsuka tiger shoes, which I'm going to call from now on tigers. It was around here, so that implied that the person who stole the cashews was wearing these Onitsuka tiger shoes. And then the question is, who did that? Well, it turns out that Uma Thurman in movie Kill Bill, and her nickname there is The Bride, she wears the tigers 100% of the time, right? However, your lecturer also wears these tigers. I'm not wearing them at the moment, but some of the people might have seen them on me. And your lecturer wears these tigers 30% of the time. So the real question here is, who stole the cashews? So I think you all by now know what the true answer is going to be. So does somebody, okay, we have somebody in the chat suggesting. Aha, Momo is just saying nice. So Momo, since you are there, can you jump in and tell us who do you think stole the cashews?
Well, I don't think Uma Thurman has been in the NSO at all. So my prior tells me that we've never seen Uma Thurman around. So I don't think you've done it, but evidence points toward you.
Okay, very good. Yeah. That's exactly what I wanted to hear. So of course that every reasonable person would not assume that Uma Thurman is the thief of who stole the cashews. So of course that everybody, given the choice between these two characters, is gonna suspect me. And I just use the cashews because I'm a cashew fanatic, and I really like the cashews. So it's not really implausible that I would snatch them if they were not well protected. But let's try and understand this let's try and write down these probabilities in so-called what I'm calling here ASICS notation, right? So what these probabilities here are telling us is just the probabilities of seeing the ASICS print, the tiger's print, given that any of these two characters appeared next to the cupboard and stole the cashews, right? So the probability of seeing tiger's mark, given that Ivan did it, would be 0.3, and the probability of seeing the tiger's mark, given the bride was there, would be 100%. But we are not looking for this. We are looking for the opposite thing. We are looking for the probability of each of these two separate characters actually stealing the cashews, given that the tiger's mark was there. And now the question becomes, what do we need to do? How do we calculate these probabilities down there? And for that, we use the so-called Bayes theorem, which is a super simple, super easy, super beautiful, and super informative theorem written by English mathematician and priest Thomas Bayes. I think it's Thomas Bayes. And I also have a soft spot for scientists who were also priests. So, but we'll talk about it some other time. So, what this theorem tells us, and I'm going to write this in this specific form here, and now I'm abandoning the ASICS notation, and I'm using something that we actually want to do. So, I'm using the data and the model. So, what it tells us is the following: the probability of our model, and in this case, model can mean multiple things. But in this case, our model can be our hypothesis, or it can be specific values of the model parameters, or can really be one model versus the other model, and so on and so on. Given the observed data, D is proportional to probability of the data, of obtaining specific values of the data, given the model M, or given the model parameters M, or whatever you want, times the probability of this model before any measurement. And this is something that we call prior or a priori probability or something like that. It illustrates our previous knowledge about the problem, right? This probability of the data given the model is something called likelihood, okay? And the probability of the model given the data, which is something that we want to find, is something called posterior or a posteriori probability. And then there is this normalizing factor here that is usually the least important, because in the most problems of the interest, it will cancel out. However, in some cases, like for example, when you want to use model selection and stuff like that, calculating this probability in the denominator is very, very important. Okay, so this is just a very simple theorem that gives you the relationship between some probabilities that are important here. Okay, and for example, we can use now this Bayes theorem to solve many problems that we have here. For example, we can use it to compare the probabilities of two discrete events. In this case, two discrete events are Ivan stole the cashews, the bride stole the cashews, right? We can use it on the continuous variables to find the most probable values of the parameters, which is something, for example, that we started from. We were doing some measurement. We wanted to find the value of the parameter in our model, right? We can use it to compare different models. Like, for example, if you really wanted to do detailed model comparison between the linear relationship in the Hubble law and the quadratic one, which would tell you whether the universe is expanding in an accelerated fashion or not. For that, you would have to do model comparison, and so on and so on. So let's now go and let's try using the Bayes theorem to solve some of these problems that we were facing so far. So first of all, let's use it to solve this cashew stealing problem. So now I can see that the probability of the bride or Uma Thurman stealing the cashews, given the tiger's print, is equal this likelihood here, which is 1, times the a priori probability of Uma Thurman being here, and as Momo pointed to us cleverly, is that probably she never stepped her foot in the NSO. And I mean, to be completely honest, the bride is a fictional character, so we can't really have any a priori probability of her committing this particular crime, right? However, I'm at NSO fairly often, and I wander around a lot, and everybody knows that I'm not the smallest person around, so I do like to munch on various kind of foods, so we can set the prior, if we only have the choice between these two options, then the prior probability for me would be something around 1. Obviously, in this case, I can't just, if I want to get exact values for these two probabilities, I can't just multiply these values. I actually have to calculate this constant in the denominator here. And if I do that, I'm gonna obtain 0 and 1. Okay, I apologize for this, but there was a question.
Bo just said we don't want the bride at NSO.
Okay, yeah, very good. But now help me change that, change the video. So how do I go back? 1 second. What's happening with our video here?
I think you changed workspaces.
Yeah, but I don't know how to change it here. Do you know how to change it on the MacBook?
There should be some way to.
There it
yeah,
is.
there you go.
Three fingers. Okay, very good. Okay, but this illustrates one very important point that you're maybe going to use very, very, very far down the road, is the fact that in many cases, I don't have to calculate probabilities exactly. And Bayes' theorem, presuming that these two denominators are the same, allows me not to worry about the denominators explicitly if my goal is just to compare the probabilities. And in a little bit, we're going to talk about something called Markov chain Monte Carlo, and the Markov chain Monte Carlo works on that assumption. Okay. However, let's go back to a more serious problem, which was our measurement here. So what we wanted to find is we wanted to find the peak of this probability on the left. So the probability that we are interested in is for which value y true, given the measured quantity, given the measured vector y, is this probability the greatest. However, that probability depends on 3 factors. One is this likelihood, which we were talking about before. One is this a priori probability. And there is this normalizing factor here, which in case that we have settled on our model, and now notice the difference. Before I was talking like about 2 competing theories, or let's say 1 model with 2 discrete options. Now we have 1 model with continuous options, right? So now these probabilities sort of have a different meaning, right? Before I was working with actual probabilities, now I'm working with probability density functions. And you will see now that it is really a probability density function. So I'm going to neglect this normalizing factor here. Let's pay attention to these other 2 quantities. So first, the prior probability, which is P of y true, is very interesting. And usually the people who complain about Bayes' theorem are going to tell you, well, by introducing these priors, you're introducing your own biases and, your own unscientific statements and so on and so on, which I'm not going to comment on because we might start arguing a lot, and it's better to always do it in person. Okay. What I want to say is that sometimes you have to use these priors because they contain important physical information. Like if you're measuring mass, your prior probability distribution, your prior assumption is that mass cannot be negative. And for example, if you're measuring some very small mass with very big spread, you have to exclude the negative values, and these priors allow you to do that. Does anybody have any example on the priors in the solar physics now?
When solving for the EMs, for example, you need to enforce the linear system solution to have non-negative values because there's no negative emission.
Yeah, exactly. For example, that, or one that I had in mind, which is a little bit different, is when you're trying to infer the inclination of the magnetic field. For example, inclination of the magnetic field is a priori more probable to be high than low, because when you draw the inclination, high inclination spans bigger circle on the sphere than the small inclination, and so on and so on. So it's an interesting thing, and if you think about your problem, you can come up with some priors. For the moment, we're going to assume that our priors are all equally probable, and this is something that is called uniform prior, or sometimes even flat prior, or something like that. Okay. And if this prior is uniform enough, and if your and you can eliminate this normalizing factor, then it means that the maximum of the left probability or posterior probability basically coincides with the maximum of your likelihood, right? And this is where the expression max likelihood comes from. Sorry about that. Max likelihood comes from is that we are assuming some other things, and then the maximum of our likelihood is the same as the maximum of our posterior, and then we can do this kind of inference. So now we know what we want to do. Now the question is, what are we actually doing? So again, what am I doing here is I'm looking at the maximum of the function p of y true given y. So in this case, it's a probability density of one variable, right? So we are looking basically for the maximum of the likelihood function in 1D space. And no matter how many measurements you have, 2, 3, 20, 500,000, you are looking for the maximum in one thing, in one dimension, basically. And this is why, since we are looking for the maximum of the function, I will stress later that it's not only maximum that we want. That is why actually the most fitting problems reduce to optimization problems. So you write down some function, and then you find the maximum or the minimum of that function, and that's what you mostly aim for. And the people who do inversions and similar things, they know this is what you do. So, however, you can also do something else. And here I'm already seeding an idea for you to consider in the future about something else. What I can do is I can just go through a given set of variables of the possible solutions for y true that I think are plausible, and I can calculate this likelihood, which should have the same shape as my posterior probability. And then when I do something like that, actually I did something like this here, and I ended up with the probability density function looking like this. So I literally went between the given set of values and found where the maximum is. And you see here that maximum is something around 10,300, right? With some uncertainty. Sorry, 10,030 plus minus some uncertainty, right? I see literally the probability density function, and I see how likely or unlikely some things are, some solutions are. Right, so here I can pretty safely say that true value is not 9,900, and I can, for example, say that 10,030 is more probable than 10,000, but I can't rule 10,000 completely. And obviously, the width of this probability is going to depend on the width of my uncertainties here, sigma, and here I used uncertainties roughly equal to 100, and here is this thing, right?
That's very flat, actually.
That's very flat because this is a very simple model, right? So for this very simple model, we're going to have a very, very simple solution. But this doesn't always have to look like this, right? But you can, you see basically now what's the advantage of this. The advantage of this is that now I'm not only minimizing one function, I'm looking for its maximum or minimum. I literally see the shape of my likelihood, and I can assess what is more likely, what is less likely, right? So if you were gambling, if we were betting on what's the true value, you would much rather prefer to see this curve than on just me telling you that the maximum of this curve is a given value. Okay? Do you agree?
10 to the minus 53 on a scale of 0 to 1.
Yeah, 10 to the minus 50. Okay, so this is because so some of you might be wondering around this 10 to the minus 53 in the exponent. As I said, I'm only calculating. In order to truly have everything in proper units, I would have to do this assessment here, right? I would have to normalize all these things properly. I didn't do that here. I'm basically just comparing the thinks I should normalize this all to 1 and then rescale. Cool. So it turns out, and now I'm gonna introduce a specific notation for likelihood. We usually use this fancy L or Markov L. So when you see the likelihood, you should know that the likelihood is the probability of getting your measurements given a value of your parameters. In this case, we only have one parameter, and this is y true. And in this case, this probability is the product of all these Gaussians and blah, blah, blah. If I take the log of this, what this product is going to turn into a sum, and basically this sum is going to be something that we call chi-squared, and that's something that you all have probably heard about. And the definition of the chi-squared is sum over all measurements observed minus predicted value for given model parameters divided by noise, and there is square missing here. I'm very sorry. So it should be yi minus f divided by sigma square. And I actually remember when I wanted to write that square, but then probably something distracted me and I didn't do it. So in the version of the slides that I'm going to put online, there's going to be a square here. Note that. What I want to stress is that chi-square, no matter over how many measurements I'm summing, is the function of model parameters. So if I have one model parameter, this is a one-dimensional function. If I have two model parameters, it's a two-dimensional function. If I have 10 model parameters, it's a 10-dimensional function. And we are looking for the absolute minimum of this thing in this hyperspace of parameters. And when you hear about people saying phrases like local minimum, convergence, blah, 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 these things are all related to some ways of traversing this chi-square hyper surface, as we call it, and finding the minimum value. Okay. And this fitting using this so-called chi-square minimization is strictly proper and strictly justified. So when our priors are uniform and when our noise is Gaussian, and in solar physics and in astrophysics in general, that is very often the case, not always because it's really true, but very often because we don't know what else to put there. There is simply the modeling things in a more sophisticated way would be just so demanding and so hard that we just regress to the simplest case, and there's nothing to judge, but you should be aware and you should try to do things in a better way when you can. And we talked already about the situations when the priors are not uniform and your noise also might not be Gaussian. If you're measuring some very low number of counts, it's actually going to be Poissonian, right? And there is also another quantity that you might be familiar with. It is so-called chi-square reduced, which is basically normalized chi-square. You take the chi-square, you divide it with number of measurements minus the number of parameters. And in principle, for good models and for good fits, this should be roughly 1. If it's less than 1, it means that either you have overestimated your noise, or you are using too complicated model, which is so-called overfitting your data, and vice versa. If it's too big, then it's if it's much bigger than 1, then it means that you have maybe underestimated your noise, or you're using too simple model. This is sometimes good, sometimes it's very hard to use because sometimes we are using simple models and we are aware of that, but we can't do anything about it. So for example, when you do Stokes model fitting, you're very often, as we're going to do in a week, we're going to try to fit some things using Milne-Eddington approximation. We won't be able to get low chi-squares until we are dealing with a very, very noisy data. So it's very hard to obtain, and strictly speaking, this chi-square is chi-square reduced should only be used when your models are linear. And I'm going to send you, together with this paper, I'm going to send you another paper which I also like a lot, which is called Do's and Don'ts of Reduced Chi-Square, which really tackles all these methods. And if you are into fitting and model assessment and so on, you might find it useful. Also, let's advertise that as well. Proper way to assess whether your model is good or not is to use something called cross-validation. And this cross-validation is also described very nicely in one of these lectures by this guy, David Hogg, that I mentioned before. And it's really nice and actually, when you listen to it for the first time, you understand, you finally understand everything. So yeah, I really recommend you take a look at that. Okay, so now let's talk a little bit about, actually not about, let's just mention some numerical stuff. So once you settle on all these things, you write down your likelihood, you write down your chi-square, basically minimizing the chi-square becomes a numerical problem. And we usually solve it by some sort of minimization, and usually this sort of minimization is some sort of gradient method or Newton method or something like that. And basically you won't, in the most cases, you won't have to think about it, because now we are happy to have Python and IDL and MATLAB, which contain various routines which do this fitting for us, so we can rely on that, and then the things are going to work. So for example, if you're a Python user, SciPy, optimize, minimize will do a good job. But also if you use very specific models, you might want to write your own minimization scheme, and it's a good practice to understand how these things work, especially for for the models which have multiple parameters, because then you can see what is happening. But there is also this thing called sampling, and sampling and minimizing chi-square are two different beasts, and we will go back to this soon. I just want to go back to something that I mentioned now, and that you hear. Actually, also heard me made a bad joke a few weeks ago about linear models, and so you hear very often people say linear models. What's a linear model in the context of fitting? A linear model implies some linear dependence, but linear dependence between what?
It's just a linear combination of any functions.
Exactly. So it's a linear combination. So your parameters, your model parameters are entering your observable in linear fashion. Right, exactly. So the model itself, the relationship between x and y, I call them x and y for generic values, does not have to be linear, right? Because x and y's are constant values. X and y's are measured. Unknown things are model parameters. So in these two examples, A, B, C, and D are unknown parameters, and they are entering our model here in a linear sort of way, right? No matter that I have like x squared and e to the x, they're entering things in the linear sort of way. However, this function underneath is arguably simpler. It's just a polynomial, but my parameter A is entering both as a square root and linearly, and then this would be a non-linear fitting, right? And the way to see the difference between these is just to write down expressions for your measurements. So let's say if we have a linear model which is a line which is kx plus m. If I have n measurements, and I can write these n measurements like this. Obviously, the best solution for, okay, it's maybe not obvious, but the best solution for my k and m is to solve this linear system. So keep in mind once again that y1, y2, blah, 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 yn, and xy, x2, xn are all known quantities, they're constants. K and m are unknowns. And this is now a similar linear system as we had when we were talking about modulation and demodulation. And we can solve it. We don't have to do any fitting, anything. We can just solve it using the pseudo-inverse. And pseudo-inverse, and now we don't have time to talk about it, and I also don't know how to prove it from the top of my head, but you remember maybe that Valentin said that using pseudo-inverse guarantees that the solution of this linear system is the optimal one, the one that satisfies chi-square equals to min. And so now imagine that I replace this kx plus m with ax squared plus square root of ax, right? So what I will have here is ax1 squared plus square root of ax1, and so on and so on. And I would have a non-linear system of equations, right? And it would be much more tricky to solve that problem. And actually, I don't even know if we could solve that problem directly, or we would have to use some minimization method for that. So this is the fundamental difference. So solving linear fitting with linear models is much more simple. Okay, cool. But still, regardless of what your model is, and I want to talk about this a little bit more, it's always better if you can afford it to, so to speak, sample. And by sampling, I mean you don't only look for the minimum of the chi-square or the maximum of your likelihood, you go through your parameter space, and that gives you the insight in the full shape of your chi-square surface or likelihood or posterior or whatever. And there are multiple reasons why that is good. One way is what I was talking about here. So looking at this, let's say that we now have to bet whether 10,000 or 10,030 is correct value. Like, I would maybe have some arguments to think about betting on the value of 10,000 or 10,050 or 10,028 or something like that. However, if this distribution was much more narrow, I would be much more certain about. I would be much more confident in the location in the value which is in the maximum, and I would be much less likely to bet that true value is 10,000 or 10,050 or something like that, right? So knowing this shape is very important. Also, it could be, for example, that the maximum is not so well defined. The maximum of your likelihood could be very flat and make multiple values very equally plausible. And you want to know that by sketching this distribution here, right? So where were we? We were here. Basically from this shape of this distribution, you can infer your uncertainties, and your uncertainties are I can't mark the text. Your uncertainties are really essential. So when you publish the paper, it's always much better to say my magnetic field is 1,000 plus minus 200 Gauss than just saying my magnetic field is 1,000 Gauss. Because if you say 1,000 Gauss, then people don't know whether the uncertainties are that are 10 Gauss or 100 Gauss or 1,000 Gauss or 5,000 Gauss. And it really helps your cause much more. And people hate, go ahead.
In the past, this was a reason for rejection.
Yeah. So probably with time we grew more soft. Like when when we are in the university, we hated these things, right? So people, I mean, I love these things, but it's always like a pain in the neck when you go to do a lab and then they tell you, well, now you have to, calculate the uncertainties. You'll be like, why do I have to show it, and so on and so on. But it's really essential to show it. And like, for example, when you want to say magnetic field here is stronger than the magnetic field here, you need to know the uncertainties, because that will support your conclusion, right? If you say it's 1,100 here and 900 here, if your uncertainties are 500 Gauss, your conclusion doesn't make any sense. Okay? And also, for example, sometimes you will encounter the likelihoods which have multiple maxima, or in this case, in the case of the chi-square minima, so that's also an interesting thing to spot. Okay. And then if you do this sampling, and here what I did was I did the sampling very naively. I just chose points here, equally spaced, I calculated probability for all of these, and I see where the value is around the maximum. But in principle, there are better ways to do that, and we're going to try to do that next Thursday. If you do sampling using one of these methods, you're going to end up with some plots looking like this. On the left-hand side, we see a probability density plot in the space of two parameters, intercept and slope. And here, not only that we see which values of intercept and slope are more probable and less probable, we also see which combinations of these parameters are more probable and less probable. And the fact that this ellipse is inclined in a specific way in this phase space tells us that these two parameters are that they are degenerate, that they depend on each other, that they are not completely independent. Not meaning that they are physically connected, just meaning that when inferring these quantities from these measurements, you get the two quantities which are, as we would call, degenerate, but not degenerate inherently, but probably in this case degenerate because of the noise, and so on. And on the left-hand side, you basically see the most probable fit, which is the thick line, and then you see a set of thin lines which basically tell you what's the spread of your most probable fit for this this set of lines here. And I also want to know the different, in most of the cases in the solar physics we will have the same uncertainties for all the points, but that definitely doesn't have to be the case. So you can see here that various points have various uncertainties. Okay. So here is a little bit more complicated model. So in this specific case, what I was doing here was I was generating some synthetic Stokes spectra of prominences, and then I was fitting them with a simple model. And as you can see here, the blue dots, which are the I, Q, U, and V, are a little bit scattered around. And I was inferring the magnetic field and magnetic field orientation. And what you see in these three density plots here are the combinations of parameters. And now you see that they look a little bit like what we saw here, but in some combinations, for example, magnetic field. So let me first teach you how to read these plots if you have never seen them before. This is something that we call triangle plots. And they're called triangle plots because they look, or corner plots, actually is maybe better way. They're called corner plots because they look like one corner of a big square. And actually the dimension of this triangle or corner is equal to the number of your parameters. So here I was interested in three parameters: magnetic field magnitude, magnetic field B, magnetic field inclination, theta B, and magnetic field azimuth, chi B. Right. And these density plots show you, let's say, the probability density of the combination of parameters. Right. And what I see, for example, in this one top density plot shows you the correlation between the magnetic field, which is on x-axis, and the magnetic field inclination, which is on y-axis. And we see that it's not even an ellipse. There is some sort of degeneracy, and this shape is very often called the banana shape, right? And I see basically that plausible values for my inclination, for example, range between maybe 80 or 70 something degrees to 88 degrees. But for a given value of inclination, I have more or less probable values of the magnetic field. And this, of course, makes a lot of sense because for the most of the Stokes parameters, what comes into play is the combination of these two parameters. So of course, they're going to be degenerate to some degree, and the noise included in the observations, existing in the observations because of our finite precision, is going to emphasize that degeneracy. And so now I have these other combinations, like for example, magnetic field and azimuth and inclination and so on. However, then you have some sort of just curves. So these curves are so-called marginalized probability, and technically even these density plots are also marginalized. So these lines here are marginalized probabilities for individual parameters. So if I ask you, or if you ask me, what is the magnetic field here in this profile, I will go to this very top line curve here, and I will say, well, it's this blue point, this blue line here denotes the median of this distribution. The median line somewhere around 3 Gauss. So it's 3.3 Gauss plus minus 1 Gauss in this case. And don't be surprised that these very low values, these are really reasonable values for the prominences, and it doesn't really matter because this was a prominence made by hand, and so it doesn't really matter. But these are, and now this is very important, this expression marginalized. So marginalized is I want to talk more about that, and we're gonna now move to marginalization. But before, let's talk a little bit how we obtained it. So very often you're gonna hear about this Markov chain. I said Markov chain, which is pretty cool, but Markov chain Monte Carlo methods, which are very nice and very useful sampling methods, which allow you to basically save some time. Naively, if you have your parameter space, what you could do to probe this, to find the distribution of your chi-square hypersurface, what you could do is just, sample it evenly, so divide it in many small hypercubes or small hypersurfaces, calculate probability for each of these elements, and then find the distribution. However, that is very expensive. Why is it very expensive? Well, to calculate this nice plot here, I used like 200 values. If I had 2 parameters, I would have to use 200 times 200 values. If I had 3 parameters, I would have to use 200 times 200 times 200 values, which is already 6 million values. So imagine now for 10 parameters. I would have to use many billion values, which immediately becomes completely prohibitive, both in terms of memory space, computational time, everything. Markov chain Monte Carlo methods give you clever way to travel through this phase space, and you have these small things called walkers. So basically, you have a point which is somewhere in your phase space, and there are some rules how to move that point through the phase space, and it's gonna move randomly, but with some conditions. And simply the points that are more often visited are going to be the points where your posterior or likelihood or whatever you're maximizing or sampling in this case are going to be visited more of the time. These things are very easy to code in their basic form, and their basic form originates from 60s and 70s or even early from the papers of Metropolis and Hastings. And they are very good because they work for all functions. So no matter how complicated your model is, you can use the Markov chain Monte Carlo sampler to sample that, to sample your chi-square surface. The drawback is that it still takes a lot of time. Not as much as you just wanted to, grid your phase space. But if you just want to send the Markov chain Monte Carlo walker, it doesn't take so much time. And the rough idea how they look like is something like this. So these 3 paths here on the left are the paths of different walkers, and now you see that these walkers are, they started from some faraway points, but they are eventually moving. And the way that we don't have the time now to go through the way that they're moving. It's very easy, and you can find it in the paper that I have sent you. We will use. I'll move later to what we are going to use. But you see how the walkers are going around, and they're going to be more often in the places which have higher posterior probability. They're going to be less often in places which have lower posterior probability. And now look at the final result when they accelerate these iterations. You have this nice Gaussian, 2D Gaussian-like shape, which exactly tells you how is the probability of having various combinations of these parameters, which are called here mu and sigma, how it is distributed in the phase space. And this is really beautiful, and this is really useful because now it looks nice and Gauss-like, but it could be a very awkward, like, these banana shapes here are not very friendly. They're not very Gaussian. It's not very trivial to understand what they mean. Okay, so now this very often people are going to say, oh wow, so you're using Markov chain Monte Carlo, that means you're Bayesian. It doesn't necessarily mean that, right? So to be a Bayesian is a state of mind. Okay, I'm kidding. In principle, it means that you have to be objective. So probably a lot of you, when you just think about an inference problem, either in the everyday life or in the science, you're probably already Bayesian, even though you maybe don't even know that, right? And for me, the favorite shape, being Bayesian is basically just applying properly conditional probability. So when you are going, even for example, let's say if I go home now on my bike and I break my glasses and forget them, I will still be able to figure out what most traffic signs mean simply from the context of where they are and what their shape is and so on. And I'll actually get to see what it says there, right? So in principle, being Bayesian for me, and this is a little bit, subjective, means 3 things. The first thing is to properly take into account the prior probabilities that are maybe important for your problem, right? So if some values are more important a priori, some are less important a priori, take it into account. Then it means don't only look for the maximum of your posterior. Cast this thing in the probabilistic way. Say the probability is 95% in these and these limits, or my posterior probability looks in such and such way, and so on and so on. And one thing that is maybe also, I mean, it's not the most important, but is also important, but I didn't mention it so far, is marginalize over your nuisance parameters. And we didn't talk about this, so we're going to talk about this now. So, and we're going to use this next week, this marginalization thing. So sometimes we have fit parameters. Sometimes we have fit parameters that are important for the fit itself, but we are not interested in their value when it comes to answering our scientific question. So let's consider this, simple example where we have the linear. We are assuming a linear relationship between the distance to a supernova and its radial velocity with respect to us, right? And in principle, the theory predicts that it should look something like this. That the velocity of the supernova should be linearly related to the distance, and I've also added an offset here. And this offset can be here because of a number of reasons. It can be because of my calibration is not perfect, because the Earth is moving systematically and I'm not taking that into account, and so on and so on. So in order to have appropriate, nice fitting, I want to take this slope into account. But this slope is not what interests me. What interests me is this value H0, right? The Hubble constant, right? So when I do this fitting, I'm going to basically obtain something similar to these plots that we have seen before. And now I want you to pay attention to the left one, where now, of course, I use the same plot, but you understand that it has a different meaning now. Now what this plot basically tells me, it tells me down up to a constant, it tells me the distribution of the probability of these pairs of V0, which is this offset velocity, and H0, which is my Hubble constant, right? So now, since I'm interested, what I'm interested in, I'm not interested in the offset velocity, I'm interested exclusively in the Hubble constant. What I should do is I should perform something called marginalization, which is basically just an integration in this space V0, H0, over my nuisance parameter, which is in this case V0. So I want to integrate this probability, this density, this probability density, which is in 2D. I want to integrate it over one dimension and obtain it only dependence on H0 and analyze that. And now you maybe understand how these things came to be. So I'm interested in 3 parameters here, right? And what are my walkers in this case doing? They're walking through the 3-dimensional space. And then what I'm basically doing is I'm saying, well, okay, I'm just gonna ignore, when I want to find these marginalized distributions, what I'm gonna do is I'm just gonna ignore 2 axes and focus on the one that interests me. So each of these distributions here, this is basically the distribution. Each of these line plots here is, so for example, for the parameter B, this is the distribution of the walkers in the phase space, looking only over the distribution over the magnetic field. I don't care how are they distributed in the 2 other ones, and this marginalization is automatically performed for me because this is like Monte Carlo solving of the integral, right? And this is super powerful, and this is super easy to do, and I'm going to show you next week how you can do that, and you will be able to fit whatever you want using Markov chain Monte Carlo. And it's going to be super powerful because you will be able to investigate all the properties of your noise, all the influence of your noise, correlations between the parameters, and so on and so on. So you can and you can have very complicated models which have a lot of nuisance parameters and just integrate over them, and you will be able to obtain you will get the probability density functions of the parameters that you want. So in the case of solar physics, one particularly annoying and but necessary nuisance parameter is this microturbulent velocity that we were talking about before. So it's necessary for us to reproduce the shape of our lines, but we don't know how to use it yet. There might be usable physical information hiding in the values of the microturbulence that we are finding. But for the moment, we are interested, let's say, in magnetic fields, velocities, and so on. Microturbulent broadening is not relevant to us, so we just ideally, we should marginalize over that, right? So to summarize, whenever we are measuring something indirectly, so it's not that you go there with your ruler and you measure the width of the table, you are going to use model fitting, right? So model fitting is, in a way, synonym for indirect measure, okay? And sometimes it can be very simple and linear, like, for example, when you just measure something a few times, you want to find the true value. Sometimes it's going to be very complicated. So, for example, this thing that we call spectral polarimetric inversions, which we were supposed to tackle in this upcoming workshop, which was now postponed. So, if you didn't see that, yeah, we had to postpone the Dickey's workshop number 3, which was going to be dedicated to so-called Milne-Addington inversions, but because of this state of emergency and the pandemic, we are postponing it. But we will tackle some of these things during the course, don't worry. So these things can be very complicated, very nonlinear, with very numerically demanding models, and so on and so on. And the idea is, the first thing that you want to do is you want to maximize the posterior probability. And in the case when your uniforms, when your priors are uniform and your errors are Gaussian, that's going to reduce to minimizing chi-square. So the so-called chi-square or least squares fit, right? We call it least squares because there is difference between the observed and the modeled value, and then square, right? And then if you're only interested in the chi-square minimum, you can just use an optimization method to find that minimum value. But if you can afford it, then you can sample and you will obtain the full shape of your posterior function, and then you can analyze it and learn much more. So for the next week, Thursday, and I suggest trying that already now, I want you to install this package called MC. I'm linking directly to how to use it, but if you just go to this web page, it will also take you to the information on the installation, and so on and so on. So there you will be able to see that. So we will spend a little bit of time just introducing our model. Our model is going to be very simple. And then the rest of the time we're going to spend doing various approaches for fitting, analysis, and so on. So, okay, very good. Any questions, any comments, any observations? Okay, if not, then yeah, keep in mind our program for next 2 weeks. We're going to have hands-on next week, and then these same hands-ons week after that. We might end up working a little bit longer than 75 minutes. I hope that's okay. If not, you will have everything recorded, so you can review that later. I will stay online after that so that we can discuss a little bit, since we are not meeting in person almost at all. And I will also send you a detailed email today with instructions how to install, what to try concerning this fitting, and also the other hands-on that we're going to do, which is going to be about line formation. And I will also point you to some of the interesting resources, because I predict that we are all going to be inside much more in the upcoming weeks, so that gives us all a chance to read many interesting articles and stuff like that. So yeah, hope you are all doing good, and see you all online. Take care.